Hello, my name is Matthew Claar with the SRI Bridges program out of SIU Carbondale. My presentation is the effect of herbicide drift on insect diversity with Samuel Ramirez and Dr. Carly Gage. I'd like to start today by showing you a quote I found in a Forbes article published in 2019. Every season, pollination from honeybees, native bees, and flies deliver billions of dollars in economic value. Between 235 and 577 billion worth of annual global food production relies on their contribution. This means even a 1% loss in production could be the equivalent of 2.35 and 5.77 billion worth of food production gone. Weed management can happen in multiple ways. One of the ways that you can manage weeds is with the use of herbicides. However, when you use herbicides, you can create sets of problems of their own. One of those problems is weeds that are resistant to herbicides. Some weeds are resistant to glyphosate herbicides, which is why we use Dicamba and 2,4-D. Dicamba and 2,4-D work by mimicking a naturally occurring plant hormone called auxin and cause the plant to grow in unmaintainable ways. The bottoms of the leaves can grow faster than the tops, and it will create like a cup in the leaf, for example. One of the other problems that using herbicide can create is off-target movement through drift events. There are two main types of drift events. The type of drift event that we look at in this study is particle drift. Particle drift happens at the time of application due to many factors such as wind, humidity, angle of the sprayer. The other type of drift is vapor drift. This happens in the hours after application. The time varies from herbicide to herbicide, but there's a window that these chemicals are more likely to drift due to evaporation, volatilization, and sometimes that can happen. The objectives of this study is to better understand yield losses from fields that have been exposed to drift, as well as the damage to pollinator habitats and communities that have been exposed to drift. This slide and the next slide were prepared by Samuel Ramirez. As you can see, we are working at the Cohen Research Facility. This is the field that we work out of. You can see that there's 13 plots, 101 through 104, 201 through 204, and then 301 through 305. Each of these subplots is broken down into, plots is broken down into 5 subplots, 101-5 through 101-45, as you can see at the top of this slide. And then each of those subplots is broken down into 3 transects, transect A, transect B, and transect C. As you can see in these pictures, the one on the left depicts the field. You can see the arch. The one on the right, as you can see in front of my feet, there's these 2 flags. This designate the beginning of transect A, these 2 the beginning of transect B, these 2 for the beginning of transect C. Some of the methods that we're using is weekly visual assessment of plant injury due to herbicides, quantity and quality of the flowers in these plots, and then the particular observations that I'm doing are of the insects in each plot to better understand the diversity that we find in these plots. So in conclusion, during my time working, I've learned how to set up experiments, work as part of a team on a group project, collect data in the field, set up in the lab, among other things, all of which that are going to help me moving on in the future to set up a project of my own. Moving forward, I will continue to collect data on this project and hope to come to a better understanding of the effect we may be having on our pollinators. I'd like to thank my wife for all of the support that she's given me through the years and everything that I've put my mind to. Dr. Lakshmi and the entire SI Bridges staff for the opportunity, mentorship, and guidance that you've provided to me over the last few months, as well as Dr. Gage and Samuel for the guidance and the help that you've provided over the last few months. If any of you have any questions, now is a good time. I hope you enjoyed this presentation, and thank you very much.